Good morning, guys. We're going to talk about accuracy and precision today, along with a little bit of math review. I'm sure you guys are probably pretty good at this stuff by now, but maybe not everybody is. So we're going to go ahead and just start from the beginning with accuracy and precision. We'll do a little bit of sig figs, a little bit of scientific notation. So hopefully today is an easy lesson and just kind of refresh your mind, get you woken up and back ready for school this year. So I'm going to go ahead and turn off my camera here and just talk, and we will get through the lesson. All right. So first thing we're going to start with is accuracy versus precision. This is actually really important in physics and engineering because there's a big difference between being accurate and being precise. So when you're taking measurements on something and you are repeatedly getting the same numbers over and over and over, but they're not directly on the known value, that's called precision. Okay, so if let's say we're launching rockets and you keep getting the same distance over and over and over, but you know that it was supposed to be something else. That means that your measurements were precise, but they weren't accurate. So precision has to do with like a grouping of numbers that are similar to each other. Accuracy, on the other hand, is talking about how close you are to your actual value. So accuracy can be shown through just one measurement. So if you take if you shoot your rocket off one time and it lands in exactly the expected place, the right distance, you could say that that's an accurate measurement. So over here on the side, you've got some examples of that. So accuracy can be dead on. It's right in the target that it's supposed to be at. This one would be an example of being accurate and precise. So you have a grouping that's all together, so that makes it precise, and it's right on target, so that makes it accurate. Down here, we have precision, but not accuracy. So you have a grouping, it's a tight grouping, but they're not really where they should be. And then over here, this one's just all over the place. So this measurement would be not precise and not accurate. So some other examples of that. If you had two different technicians taking samples, you can see that technician one has a lot of really good measurements here. So whatever measuring instrument they were using gave you a lot of precision in the measurement. You can tell that by the fact that it goes out 3 digits past the decimal. So whatever scale this was, or whatever measuring instruments they were using here to calculate the density, really gave them a lot of information. So all these numbers are very close to one another. So this group of numbers is very precise. But if you go over here, it says that the accepted value is 2.6 grams per milliliter. So these are not close to 2.6 grams per milliliter, but they're close to one another. So this grouping would be considered precise, but not accurate. Over here, you have technician 2. These numbers are much closer to the accepted value, but they're really not that tightly grouped together. So you have more accuracy with these numbers, but I would say less precision. So this is more precise and less accurate, and this would be more accurate and less precise. So the reasoning for that could happen, you can get a tight grouping of numbers that aren't necessarily on target whenever you have maybe your measuring instrument needs to be recalibrated or it's not being read correctly. So if this happens and you are calculating the speed for something or the acceleration for something, and over and over, your group is getting the same measurements, but you know that they're not right. You've talked to other people in the class. You know what the calculated value is. You know what should be. That could just be like a problem on your part. It could be a measuring instrument issue. It could be the timer is wrong. It could be that the person starting and stopping the time is not doing it exactly when they should be. So if you get a situation like this where you have a nice precise grouping, but you know that it's not meeting up with the known value, revisit, look at your instruments, kind of check and make sure that you are measuring things correctly. So with that, we have percent error. Also pretty important in physics and engineering as well. So you need your measurements to be within a certain threshold. in most cases, there's a little bit of wiggle room. So that's where our percent error comes from. And there's normally a threshold, 5 to 10%, probably less than 5% is common. But the further you get away from the accepted value, the more error you have. So that could make a lot of things not work correctly. So here, to calculate your percent error, you're going to have the measured value, which is the value that you have measured, subtract the accepted or the known value, and all that is over the accepted value again. And then you multiply that by 100 to get a percent. Okay, so knowing this, you will have a positive or a negative answer, and leaving those marks on there is important. So you do need to designate if it's positive or negative. So if your answer is positive, it means that your measured value was higher than the accepted value. And if it was negative, it means that your measured value is lower than the accepted value. So an example of that would be something like this, a very simple question. So if a student measures the density of an object as 1.40 grams per milliliter, the correct or accepted value is 1.36. So what is the percent error of the student's measurement? So we just drop these in here. So 1.40 is the measured value. The accepted value is 1.36. So we plop that in here and down here, multiply it by 100, and we get 2.94%. So since this is a positive value, we know that this is saying that the measured value was almost 3% higher than the known value. So another one, we're going to just do this one together. All right, so I'm still getting used to my little writing tablet, so please forgive me if this is messy. It will get better, I promise. So what is the percent error for a mass measurement of 17.7 grams given the correct value is 21.2? So you measured, oh geez, sorry. We'll go back here. Let me turn on my pen. That's important. Okay, so you measured 17.7 and the known value was 21.2, right? All of that is going to be over the known value of 21.2 multiplied by 100, and this is going to give you your actual value. So believe it was right in the range of 17%. Okay, so we know, and actually this is a negative. So we have negative 17% is our percent error. This is a huge percent error. This would probably be a value that it would throw a red flag for you. So if you're getting this kind of percent error in your measurements, this should tell you that something is wrong. So the measuring was wrong, the calculations were wrong, something was wrong. This gives you reason to go back and look again. And again, the percent error threshold will change depending on what you're working on. Some things require more precision. So just an example of that would be, let's get this back on here. An example of the precision level, like my brother, he is a precision machinist at Boeing. So when he writes the programs for the machines, and they have to cut pieces very, very specifically. He works in the Phantom Works department, so he's working on things for the military a lot of things he can't really tell us any details about, but they're cutting things like titanium, and it's very expensive, and they need to make sure that it is right the first time around. So they cut practice pieces, and they measure their percent error. They make sure that all of the pieces work together very well, and the percent error has to be very close to zero for that. These large machines with lots of many working pieces, it has to be right on target. So that's an example where you have very little wiggle room. So it really just depends on your situation. A lot of times you'll get sets of data that have a pretty wide range, and they're considered within the threshold. So we'll just have to, you kind of determine that depending on what project you're on. So anyway, with your error in measurement here, so that all being said, you do have some leeway in your measurements. So whenever you are taking measurements, so this one here, let's say you're just measuring the length of something, you can see that this falls right between 6.3 and 6.4. So you as the scientist or the engineer, if you do not have a measuring instrument that is more precise than this, so you don't have anything with any more markers on it, you can take the liberty of saying, okay, I'm going to say that this is 6.35. So you do have the ability to guess one extra number. Same thing goes for massing. So if you look at this picture, it's 10.27. Oftentimes, especially in our labs here at school, these scales have been used for years and years, and some of them just aren't as precise as they used to be. So sometimes you'll get it where this last digit keeps fluctuating. It'll fluctuate from 5 to 6 to 7, 8, 9, and it just keeps jumping back and forth. If that's the case, you do not have to try to remeasure it a bunch of times or wait for it to settle, because it probably won't. You can just say that you can guess it, give it your best guesstimate, basically. So if you read this and you think that it's a 7, you can record your measurement as 10.27. So that kind of comes back to our significant figures, okay? So you do have a certain amount of certainty whenever you're measuring, and then you can add in your one final digit. So we're going to talk about sig figs. I know that you guys have probably done sig figs a lot throughout the years in different classes. I know you did them in physical science, but that might have been a little while. If you were in chemistry, you did them last year. The thing with sig figs is that significant figures are only really used in certain fields, okay? So whenever you get into different fields, like we've talked, some of us teachers have like reached out to the community, and we've talked to other professionals. Very few professions actually use significant figures. So what we'll be doing with this is I want you guys to know how to use sig figs, so that if you go into something that requires a high amount of precision, that you know how to do sig figs. But we're not going to harp on this a lot this year, because we're going to usually just use a designated value after the decimal point, so 1 or 2 numbers, and go from there. Because for our calculations in this class, significant figures are not going to change our answers. So I just want you guys to know what they are, how to use them, and just kind of have that under your belt in the future. So significant figures, your first rule here, any zeros between non-zero digits are significant. Okay, so these are all highlighted red. So you would have 5 sig figs here. Second rule is any zeros in front of non-zero digits are not significant. Okay, the reason for that is that you can write this in scientific notation and none of these zeros matter. So even though there's a decimal point, it doesn't matter. So any numbers before non-zero numbers, any zeros before non-zero numbers do not count. Zeros at the end of a number after a decimal point are significant. So what this is showing is that the measurement didn't stop at 450. Whatever measurement tool was being used had more precision and could tell you that it definitely was 450.00, that there was nothing else after that. So these are significant. This value would have 5 sig figs. Zeros at the end of the number without a decimal point are not significant. So this number, if it does not have a decimal point at the end, is saying that you're kind of giving it a rough estimate. You're saying that, I have $7,000 in my bank account. That doesn't mean that that's the actual value. That means that you're kind of guessing. You know, it's probably around that value. It's close enough. It'll, get the point across, but it's not an actual measured value. So if you went into your bank account and actually looked, it wouldn't be exactly 7,000, right? So zeros at the end do not count. So this would only have 1 sig fig. So when you're adding and subtracting for significant figures, you're going to always use the least amount of numbers after the decimal point. Okay, so not necessarily the smallest amount of sig figs, just the smallest amount after the decimal point. So you're saying that this value was measured with the level of precision to go out just one number. This one maybe was measured with a different measuring instrument. So this value was measured more precisely, but it doesn't matter because if this other value was not measured with that precision, you cannot assume that you know what would have been after that 5. So that's why your answer can only have the same value as the smallest amount after the decimal. Okay, so these numbers here, you can use them in your addition. You don't have to change sig figs until you get to the answer, but always go back and double check that you've looked through all of the values involved, and when you're adding and subtracting, you're always only just going with the numbers the least amount after the decimal. Multiplying and dividing is talking about the fewest amount of sig figs available. So when you look at these two values, this obviously has 5 sig figs, and this one would only have 1 sig fig. So your answer can only have 1 sig fig. What makes this interesting down here is because you're looking at this, you say, okay, well, that's 3 numbers. It's still only 1 significant digit, okay, because these zeros in front are not significant. So you could also turn this into scientific notation if you're more comfortable with that, because that would give you a more obvious answer of just 1 sig fig. So scientific notation, this is the last little bit here. Scientific notation will be used a lot in physics. So you do need to be very comfortable using and calculating scientific notation. So basically all this is doing is taking very, very large numbers or very, very small numbers and making them easy to use and manipulate. So instead of writing this out every time you want to communicate this number, you can write this. Okay, so it's a lot smaller, a lot less to write. You could have this value with 6 more zeros on the end. You don't want to write that every single time. So this is much easier to use to communicate. So the format the scientific notation is written in is m times 10 to the nth degree. Okay, so you have m in the front. This is any number greater than 1 and less than 10. Okay, so there can only be one number in front of your decimal point. So like this, it's 4.5. This could not be 45. And then over here, the n is how many places that you had to move your decimal point. So it's whole places that you've moved it. So when you're looking at this here, you can see that the arrows go in opposite directions, right? So if you're moving your decimal point to the left, the exponent will be positive. If you're moving your decimal point to the right, the exponent is negative. Okay, so another way to double check that is that this is a number greater than 1, so the exponent is positive. This number is less than 1, so my exponent is negative. There are some rules that go along with adding and subtracting. I know that probably most of the time, if not all of the time, you'll be using your calculators. So you probably don't need to worry about this too much, but it would be important to know how to do it in case you were stuck somewhere where you weren't not allowed to use a calculator. So when you're adding and subtracting scientific notation, the exponent values have to be the same before you do that. So you can change that, like this was 3 times 10 to the second. You can change this exponent by moving the decimal point. So we know that there's an unspoken decimal point behind this 3 right here. So you just have to move that over 1 spot to the left to add 1 here. So we moved that decimal point from behind the 3 to in front of the 3. So 1 spot to the left means we added 1 to our exponent. So now that these are the same, this can just be added in the front and then you bring this down, okay? Multiplication and division is less complicated, honestly. So multiplication, your m values, so your values in the front will be multiplied and you're going to add the exponents together. And then division is the other way around. So division is you're dividing whatever numbers are in front as you normally would, and you would subtract the exponents. And that is it for today. So please contact me if you have any questions about the assignment, and I will be available to answer them. Hope you guys have a great day. Bye.